we have, why is the ozone molecule polar? So the thing you have to recognize is that ozone, although it's technically considered a molecular element because it's all composed of the same element, that doesn't mean that it's going to be perfectly balanced. And for example, like a good example is like O2. All right, that one is non-polar because of the fact that when you draw it out, it's a double bond between them, and this is typically what oxygen looks like, so everything cancels out. But the ozone molecule, we're actually going to need to draw it out using the Lewis dot diagram and everything, just to be able to really visualize it. Okay, so if we go to the periodic table, oxygen, all right, because it's O3, that's ozone. Oxygen is a 8th element. Okay, so if we were to quickly do electron configuration, we start at helium, and the reason why I do this is because it's always good to verify that we have the right amount of valence electrons, and to understand electron configuration. We could just look at the columns and say, oh, it's column 16, oxygen has 6 valence electrons, but this is always a good way to really understand what you're doing. Because we start from helium, and it'll be 2s2, and then oxygen is going to be 1, 2, 3, 4. That's 2p4, okay? And you notice that the electron configuration also agrees that we have we have 6 valence electrons. So as the Lewis dot diagram states, you want to be able to use all those 6 from each oxygen. So we have to find a way to balance out 6 times 3, 18 electrons. Okay, so it doesn't matter which one we choose as the central atom because all of them are oxygen. So we're going to have oxygen here. We're going to start with just a single bond on each side. Okay, then we have the other 2 oxygens. All right, so now with it being said, oxygen contributes 6. So right now it's sharing 1 of the 2 on this side, which we're referring to the right oxygen. Okay, so well, 1 of the 6. So then we need 2, 3, 4, 5, 6 there. This oxygen to the left, same thing. We need 2, 3, 4, 5, 6. And then the oxygen in the center is already sharing 2 of its 6. So it's going to be 2, 3, 4, 5. Just making sure that I counted right. Yep. 1, 2, 3, 4, 5, 6. Oh, I started counting wrong. It's going to be 2, 3. Why did I do that again? It's going to be 3, 4, 5, 6. So this oxygen is content, okay? But what it could do, because as you can see, these oxygens have these radicals, these lone electrons, there has to be a way to kind of figure out how to balance it. So the best thing oxygen can do, really in this case, would be to specifically give one side that one of his extra ones, and then use the other electron to form a double bond with the other oxygen. The reason being is that if you notice, we still keep track of the same amount of electrons, but now oxygen still gets to keep its octet rule, and also at the same time it also gets to satisfy the other oxygens around it. So what we have now is oxygen in the middle, a double bond to the right, just because I chose it there, okay, and then we have oxygen to the other side with a single bond, but we have 1, 2, 3, 4, 5, 6. So if you count it out, actually, you will see that we still have 18 electrons in there. So just to be able to signify which is the one we change, we're going to put a red here, okay, because that's the double bond there, and we're going to put the red here, okay, because that way it shows all the things that kind of quote unquote moved around. So if we counted, we have 2, 4, 6, 8, 10, 12, 14. I think I'm missing. Oh, in the center, yes. 14, 16, and these will be still our 18. Just down here to mimic what we had up there. So exactly, that will be the Lewis structure for oxygen, and we can actually verify this through the electron number. So for the center oxygen, we have typically likes to have 6, okay, and it's going to be subtracted by how many does it have by itself right now? Only 2 electrons, and it's sharing around itself 6. So that's 2 plus 6 over 2, which is 3. That's 5. So this oxygen is plus 1, which makes sense. It's doing more than it should. And you notice that because we have a plus 1 and ozone is a neutral molecule, you're going to have one of the oxygens be a minus 1. Okay? So for the oxygen to the right, okay, it's going to be 6, and it has 4 by itself, and it's sharing 4. So perfect, that equals 0. So right now we have this as a plus 1, okay? And now for the last one, the one to the left, 6 minus, it actually has 6 electrons by itself, and it's only sharing 2. So 6 plus 1 is 7. So this would be the minus 1 right there. So this is where that negative charge is. So in total, it does make for a neutral molecule, but you can see how the oxygen in the middle is kind of doing more than it needs to, just to be able to keep the octet rule and keep the oxygens around it satisfied. So with all that being said, we now see that the structure for oxygen, if we drew it out, okay, would be like that. Just gonna do that. This would be the structure for ozone, okay? And right away, actually, this will actually tell you whether it's polar or not. When you have an unaccounted for lone pair in the central atom, that lone pair also exerts its own force, its own electronegativity, its own pull. It's literally like a negative charge just concentrated there. So that is what's going to influence the pull of oxygen, because now it's no longer balanced. Okay, it has two types of bonds on each side, but then also has a lone pair. But with that being said, though, if we count all three to figure out the electron geometry, this electron geometry number is 3, okay, which is trigonal planar. That is the electron geometry. And this all ties into why it's a polar molecule, okay? And then if you want to do the molecular geometry, okay, we have 2 bonds. We don't count what type of bond it is. We just know that it's 2 bonds. And we have 1 lone pair. So 2 bonds, 1 lone pair. You'll see that it's actually bent. The shape is bent. And the reason why it's bent is because of the lone pair having its own field and pull, okay? As we check the Vesper theory here, 3 trigonal planar, you'll see exactly it's bent. And it kind of looks like water, like H2O. That would be kind of what it looks like. But exactly, this is what we're dealing with here in regards to the shape. Hopefully you can see the mouse hover over it. If not, I wish I could highlight it. There we go. This is the shape we're dealing with. And with all that being said, because it's bent, it already has an uneven distribution of things pulling the oxygen atom in the center, which is why it's a polar molecule, okay? And to go beyond that, just making sure that I've covered everything. Oh yeah, in regards to this, last thing you need to know, which doesn't really affect the fact that it's polar, it's still going to be polar, but ozone experienced resonance. As you can tell, the double bond could have been on either side, where it's shared like that. Okay, and that's how you signify typically like resonance structures. But exactly, this is what you'd get. Kind of something that looks like that, because it actually forms a resonance between the other oxygens, because that double bond could have been on that would be another resonance structure. I could have drawn it like this. It's still ozone, it's just a different type of resonance structure. Hence why it kind of looks like that, where the electrons are given more space to roam around, adding to its stability, which is why ozone can exist, even though we're dealing with the fact that one oxygen is a positive and one oxygen is a negative. So with that, they explain the Lewis structure, and because it has that lone pair and the uneven distribution, exactly, this causes dipole movement, and especially because that lone pair is really doing, I guess, what lone pairs do. It's no longer balanced because the lone pair doesn't have anything to counteract that. And exactly, you're also dealing with a single versus a double bond. So the whole, I guess, molecule is, yeah, uneven distributed, which is why this is considered a polar molecule. So with that being said, let's move on to question